It's lecture 8, and lecture A of lecture 8, we're going to focus on calculations, more trigonometric substitutions, and do some basic examples with what's called the method of partial fractions, which is the last method you need to know for the gateway, which is Friday of next week, 1 week from today. And the trig substitutions actually are not in the gateway. You'll be happy to know because those oftentimes end up being kind of nasty. Though there is a certain memorized integral that, actually a couple memorized integrals you could do with trig substitutions that you should just memorize. I'll remind you of those. In lecture B, the focus will be on parametric curves and motion, as well as vectors, and the resulting integrals that we get. And the integrals are, again, typically going to be nasty, and we're going to have to pretty much rely on Mathematica to do some of them that we encounter. And I'll talk about mathematical homework number 2. In the book, in the reading, we're sort of skipping around a lot. You know, our main content is chapter 7, but we're skipping back to chapter 4. We're doing this appendix D. It's got the vector stuff. I'm also going to do a little bit in chapters 8 and 11. The idea being that I'm trying to bring in some of the applications of these ideas as early as possible. Okay, the questions related to these ideas that you'll start doing are meant to be fairly basic. More important is you understand what I'm talking about in class, and then can do the problems in those sections later on in the course. We'll come back to them later in the course, and we'll go into it in more depth, but we're getting introductions to those things right now. All right, let's do some calculations here in lecture A. So I've got 4 integrals here. The first one was the one we did in lecture 7, 7b. This one we did. I wrote solution keys for these two and made them available to you. And in class I told you what substitution to do. I will go ahead and do those in class here now. And here's a new one that I haven't done before. So we're going to do trig substitutions here. That's what the method is, integration by trigonometric substitution. Though actually in the last example we actually could avoid a trig substitution, but I will do one anyway, just to emphasize something. So let's focus on the second one here. When you've got something, a variable squared, or something involving the variable squared, plus something else squared, it turns out in that case to be good to let x equal tangent theta. In this one, it was a good idea to let x equal, 5 tangent theta in this case, since 25 is 5 squared. In this case, it was good to let x equal 2 sine theta, 2 because of the 4 being 2 squared. And you see why after you make the substitution, because when you let x equal 5 tangent theta, then x squared plus 25 is going to be 25 tangent squared theta plus 25. You can factor out a 25 and write it as 25 times tangent squared theta plus 1 in parentheses, and then that gets replaced with secant squared theta. That's why that's a good idea, and we're going to take the square root of that as well. dx, if x is 5 tangent theta, will be 5 secant squared theta. From here down to there, d theta. Now go ahead and do that substitution. Replace x squared plus 25 under that square root with 25 secant squared theta. Replace dx with 5 secant squared theta. Technically speaking, the square root of something squared is the absolute value of that thing. But when we do these substitutions, we always make assumptions about theta anyway in such a way that in this case, secant theta is positive. Secant theta is positive where cos theta is positive, which is over in the first and fourth quadrants of the plane. When you think of theta as an angle, Square root of 25 is 5. That cancels with the 5 there. If you think about what cancels here, we're left with a secant theta. Because we'll get the square root of secant squared theta, which will be secant theta, assuming secant theta is positive. And that secant theta will cancel with one of those. This is the integral we did last time that was with that crazy trick. Multiply the top and bottom by secant theta plus tangent theta over secant theta plus tangent theta, and then do a substitution. And you ended up getting the natural log of the absolute value of secant theta plus tangent theta plus c. Now get this back in terms of x. If x is 5 tangent theta, that means theta is arctangent or inverse tangent of x over 5. The tangent of that angle is x over 5. What's the secant of that angle, if you think of it as an angle? Draw a right triangle again. Label this angle theta, where theta is arctangent of x over 5. Then use your knowledge about trigonometry of right triangles. Tangent is opposite over adjacent, TOA, from SOHCAHTOA. So since the tangent of this angle is x over 5, we might as well take the opposite side to be x and the adjacent side to be 5. Again, you could use 2x and 10 or 3x and 15. You might as well pick the simplest thing possible. By the Pythagorean theorem, that means the hypotenuse is the square root of x squared plus 25. And again, that matches that. That's no coincidence that happens in these kinds of problems. The secant of that angle, 1 over the cosine, SOHCAHTOA, cosine is adjacent over hypotenuse. So flip that, you get hypotenuse over adjacent, this over that. So it looks like our final answer is natural log of square root of x squared plus 5 over 5 plus x over 5 plus c. Technically speaking, and this happened in the last example, we really don't need the absolute values here because by definition the square root symbol gives you a positive square root. This thing inside the natural log is positive, so we really don't need the absolute value signs, but it doesn't hurt to keep them either.
Shouldn't the square root be square root of x squared plus 25?
Thank you. X squared plus 25.
So if we were to be asked to do a trigonometric substitution in the future on an exam, would it be okay for us to skip doing the trick that you showed us, multiplying by secant theta plus tangent theta over secant theta plus tangent theta, just to eliminate?
Yeah, I mean, if you got that particular integral, I'd probably remind you what the answer is.
Okay.
All right, next example. This one here. In this one, it's actually best when you've got the variable quantity squared minus something else squared, 25 is 5 squared again, to let x equal 5 secant theta in this case. Again, the 5 comes from the fact that 25 is 5 squared. Then dx is going to be 5 secant theta times tangent theta. The derivative of secant theta is secant theta times tangent theta. That's something worth remembering. And x squared minus 25 will be 25 secant squared theta minus 25. 25 times, in parentheses, secant squared theta minus 1. And that is going to be the same as tangent squared. 25 tangent squared theta. So, go ahead and make the substitutions now. Let's use red here. Replace x squared minus 25 under that square root with this. Once again, we take the square root. Technically, we would get 5 times the absolute value of tangent of theta. But again, the trick is with these substitutions, assume theta is in such a domain as to make the tangent positive, so we don't worry about the absolute value sign. Probably the best justification that you can give is that it works by the end. You can always check your answer. So we end up with 5 times tangent theta on top because the square root gets rid of that square. On the bottom we have an x, which is the same as 5 secant theta. And then the dx gets replaced with 5 secant theta tangent theta. This 5 cancels with that 5. This secant cancels with this secant. It looks like we're left with 5 times the integral of tangent squared theta. How do you do that? The best way is to use the same identity. The fact that 1 plus tangent squared theta equals secant squared theta, or the fact that secant squared theta minus 1 is tangent squared theta. Replace tangent squared theta with secant squared theta minus 1. And the integral of secant squared theta is one, it's a memorized one. It's one you should memorize for the gateway. What is it? Integral of secant squared?
Tangent.
Tangent. Just tangent. 5 tangent theta minus 5 theta plus c. Get it back in terms of x. Theta is, based on this, is arc secant, which you may have never used before, of x over 5. You can replace this theta then with arc secant of x over 5. What about the tangent of that angle? You want to think of it as an angle in a right triangle. We know the secant of that angle is x over 5. Again, think, secant is 1 over cosine. Cosine is adjacent over hypotenuse. So secant's got to be hypotenuse over adjacent. The secant of this angle is x over 5. This has got to be x, this has got to be 5. It's very easy to make a mistake there, you've got to be careful. Figure out, we're going to take the tangent of this angle, opposite over adjacent, so we've got to figure out the length of this side. And if you use the Pythagorean theorem, it shouldn't surprise you that you get that, which matches this. So the tangent of that angle is opposite over adjacent, this over this. So your final answer is going to be 5 times this over this. The 5's cancel. And you're left with square root of x squared minus 25. Minus 5 times arc secant of x over 5. Plus c. Arc secant is a function you can use. Maybe you've never used it before. Question?
How did you decide at the beginning that you were going to use 5 secant?
Because it's a trick just to recognize that when you've got a variable quantity squared minus something else squared, it's best to do that because you end up using this identity. And it typically makes it easier. Because we then end up taking the square root of this. Does that make sense? I mean, it's sort of experience trying things and using identities, and that turns out to be the best thing to do. Again, when it's a something squared minus the variable quantity squared, then use sign as part of your substitution. If it's the variable quantity squared plus something squared, then use tangent in terms of with your substitution. If it's the variable quantity squared minus something squared, then use secant. It's sort of tricks of the trade. By the way, you don't have to use the arc secant. The secant of this angle is x over 5. The cosine of this angle would be 5 over x. You could use the arc cosine. Or the arc sine. I mean, arc secant of x over 5 is the same as arc cosine of 5 over x. the same as the arc sine of square root of x squared minus 25 over x. It's an angle, and you can figure out the cosine, sine, and secant of that angle based on this labeling.
I know we use the tangent, secant, and sine. Would you ever use the cosine?
You could, yep. It's just sort of standard to use sine, tangent, and secant. It avoids negative signs if nothing else when you find dx. All right, what about this last one? I am going to use a trigonometric substitution on this one, even though you don't see a square root. Though I actually could do it without a trig substitution, turns out. I will use one anyway. But before I try a substitution, I'm going to complete the square first. What do I mean by that? When you first see an integral involving a rational function, rational functions are ratios of polynomials, probably the first thing that should come in your mind is, oh, maybe I need to factor the bottom and use the next technique I'm going to show you in a few minutes, the method of partial fractions. However, if you try to factor the bottom here, you will not be successful, okay? Because the roots of this quadratic turn out to be complex numbers. It is factorable in terms of complex numbers, but we're not doing that here. So what should you do with it? You should try to take this expression, 9x squared plus 54x plus 97, and write it as ultimately something squared plus something else. And that something else we're actually going to think of as being a square as well. Out of the first two terms, factor whatever's in front of the x squared out. 9 in this case. I happen to make the numbers work out nicely because 54 is 9 times 6. So I get a plus 6x. Leave the plus 97 out there as it is. Now complete the square. Take this thing inside the parentheses, which is a squared term and an x term, and add something to it that will make it a perfect square. Hopefully you've done this before. The trick is to take now, when the coefficient of x squared is 1, take the coefficient of x and divide it by 2. 6 divided by 2 is 3. Square that number, get 9, and just stick it in there. You should have all seen that in the past. That makes that part a perfect square. X plus 3 quantity squared. That's the trick that makes that happen. But you can't just say that and be done. You have to compensate for the fact that you've added a 9 in here. And really a 9 times 9, 81 to the whole thing. You've got to subtract off 81 to compensate, to make them equal. But now we have this in the form 9 times x plus 3 quantity squared plus 16. And yeah, this is something squared involving the variable plus something else squared. Now I made the 16 a perfect square and I made the 9 a perfect square. I actually didn't have to. If, for example, that had been a 17, I would have thought of this as square root of 17 squared instead of 4 squared. But I made the numbers work out nice. So this integral is the same as the integral of that thing. 1 over, and I think for extra emphasis I'll write it like this, 1 over 4 squared plus 3 times x plus 3. At this point, the best thing to do actually would be to do a w substitution, although it would be tricky, a little bit tricky, to ultimately relate this to an integral that's going to give me an arctangent for the answer, and that the answer will involve arctangent, because you know the integral of 1 over 1 plus x squared dx is arctangent of x plus c. not a 1 there, it's a 4 squared. So that seems like it's a bit of a problem. And it's not an x squared there, it's a 3 times x plus 3 quantity squared. I'm going to do a trigonometric substitution instead of a w substitution, a simple w substitution, partially just to illustrate that I still could do the trig substitution. The w substitution would be easier and similar kind of in spirit, but I want to show you you could still get the same answer either way. When you've got something squared plus the variable quantity squared, that's when you use the tangent. We're going to let the quantity involving the variable that's squared be equal to something times tangent of theta. What should that something be? I want to use the fact that 1 plus tan squared theta is secant squared theta. It's not a 1 there, it's a 4 squared. If I use a 4 over here, if I substitute that in place of 3 times x plus 3, I will get a 4 squared involved that I'll be able to factor out. And use the fact that 1 plus tangent squared theta is secant squared theta. It's a little bit strange to write it that way, but it's okay. I can now differentiate dx d theta and put the d theta on the other side. What I would get if I do that is 3 dx is 4 secant squared theta d theta. So I need to use that fact as well. What happens when you plug this in? Here's what happens. You get that in the bottom, and the dx gets replaced by a 4/3 if you divide this one by 3. Divide that equation by 3 to solve for dx. Dx is going to get replaced by a 4/3 secant squared theta d theta. You can factor out the 4 squared there. Replace 1 plus tangent squared with secant squared theta. The secant squared thetas are going to cancel completely. The secant squared theta you get from there is going to cancel with that. There will be no trig functions left. It's going to be a really easy integral. One of the 4's will cancel. That 4 will cancel with one of those 4's. The 3 stays there. And the 4 left over on the bottom stays down there. 4 times 3 is 12. You're going to get 1/12 times the integral of 1 d theta. Because the secant squared thetas cancel and one of the 4's cancels. Meaning you get 1/12 theta plus c. Now solve that equation for theta in terms of x. Divide both sides by 4. Take the arctangent both sides. The final answer here is going to be 1/12 arctangent of 3 times x plus 3 over 4 plus c. And you can multiply that out. You can write it as 3/4 x plus 9/4, if you like.
Could you draw out a triangle so you don't use the arctangent and say, opposite over adjacent? So adjacent would be 4 and opposite would be 3x.
You'd still need to use either an arc sine or a cosine. But you can't avoid the arc function. If we had just done a w substitution based on this integral here, it would have been a bit quicker. And the right thing to do would be to let let's see, it's a little, well, maybe it's a little trickier. W equal, it's going to be 3/4 or 4/3. I think it's 4/3. Oh, how about this? 4w equal 3 times x plus 3. For dw would be 3 dx then. Dx would be 4/3 dw. You get the integral of 1 over 4 squared plus 4w squared times 4/3 dw. Square there as well. One of the 4's would cancel still. You'd have a 1/12 still. This would be 1/12 times the integral of 1 over 1 plus w squared dw. You get the same thing. That would be 1/12 arctangent of w plus c. Solve that for w. You get the same thing. It is the same answer. Both are certainly tricky, okay? It's not easy. It's very easy to make a mistake. So it needs practice. You don't have one this difficult on the gateway either. But in the few minutes we have for the quiz here, let me introduce you to our first partial fraction example. And you do have a partial fraction problem on the gateway. First example there. That's kind of similar to the previous problem, right? A quadratic on the bottom, a 1 on top. However, this quadratic can be factored. It's 1 over, we're integrating 1 over x plus 2 times x plus 3. When you integrate such a thing, what you want to do is you want to rewrite that fraction in a new form. That makes it easier to integrate. You might hope that you can break this fraction into 2 pieces, some number over x plus 2 plus some other number over x plus 3. Why might you hope that? Well, if you add fractions like this by getting a common denominator, that would be the common denominator. So maybe you can go back the other way. Figure out what constants there will be that will make this true. But we want to solve for a and b then. There are a couple different ways this can be done. I like using a little trick that is sort of a shortcut. The first thing you should do is you should multiply both sides by that common denominator here. X plus 2 times x plus 3. It'll completely cancel on the left and leave you with a 1. And multiplying by x plus 2 times x plus 3. Dot for multiply. Dot times x plus 2 times x plus 3. Dot being multiplied. Cancels completely on the left, partially canceling on the right. The x plus 2's cancel with that term, leaving you with an x plus 3. The x plus 3's cancel with that term, leaving you with an x plus 2. Now technically, the sort of more rigorous way to go about this is to completely now expand this as some coefficient times x plus another term that's a constant. And you want these things to be equal no matter what x is. And since that term doesn't involve an x, the coefficient of x must be 0. And the other thing must be 1. So there's a quicker way to find the answer. You want it to be true no matter what x is, so pick particular values of x that make those factors 0. Like -3, for example. If x is -3, then a's coefficient goes away, and b's becomes -1. -3 plus 2 is -1. In other words, b must be -1. Now choose x equals -2. -2 plus 3 is +1. -2 plus 2 is 0. A must equal 1. So this will equal that if A is replaced by 1 and B is replaced by negative 1. In other words, this integral can be thought of as this integral. And that can be broken into two integrals that are both easy to do. What function becomes involved? Yeah, natural log. Natural log of the absolute value of x plus 2 minus natural log of the absolute value of x plus 3 plus c. You can write the answer that way. You can also use a property of logs to write it another way. The difference of two logs is the log of their quotient. And the ratio of two quantities that have absolute value signs around them, you can put the absolute value around signs around the entire quotient. This form is actually a bit more useful in another new subject we're going to introduce next week called differential equations. You have a little bit of reading about differential equations, but we're going to delve into them a little bit more deeply. We're going to use the method of partial fractions to help us solve some important kinds of differential equations as our application next week. Okay? So there's our first basic example. After the quiz, we'll try to do these two as quick as we can. And we may talk more about trigonometric curves and vectors. But put things away from the quiz. Yes.